Good morning. In our previous lecture, we've seen first example of SN2 reaction, which is a nucleophilic substitution that occurs on halogenated alkanes. Today we will talk about factors that affect the success of this reaction, and we'll discuss the influence of both nucleophile and the structure of the starting. And so nucleophile clearly is a very important factor in nucleophilic substitution. If you have a stronger nucleophile, then SN2 reaction will be faster. So the definition of nucleophile is tied to kinetic parameters, which is the rate of the SN2 reaction. Okay? Now if you look at the structure of a starting material, it is pretty straightforward to conclude that if we have a more negatively charged nucleophile, it will have an easier time attacking the partially positive carbon center in our starting material. And so that indeed is the case. So the first factor is charge, okay, which means that if everything else being equal, a charged species such as methoxide ion will be a better nucleophile than its conjugated acid methanol, right? And that will be the case for many other species, and it's a general rule that a base is a better nucleophile than its conjugated acid. Now this should not lead you to believe that the stronger the base, the better the nucleophile, because basicity and nucleophilicity, although many times they coincide, they're actually fundamentally different. Nucleophilicity is defined as a kinetic parameter, defined through the rate of SN2 reaction, while the basicity is defined as a thermodynamic parameter, defined as a position of equilibrium between acid and its conjugated base, or vice versa. And so the definitions are fundamentally different. It's only coincidence that sometimes the two tend to favor the same compounds. The second factor that we'll consider will be electronegativity. We want our nucleophile to be reactive, which means it cannot be too happy with having its negative charge, which means that the more electronegative atoms will be less likely to engage in reactions and will thus be weaker nucleophiles. So if we have HO-, this will be a stronger nucleophile than fluorine. The same will apply to things like phosphorus and sulfur, or ammonia and water. Ammonia is a better nucleophile than water because it's less comfortable with electron pairs and wants to share them. Okay? The third factor, which oftentimes works in concert with this electronegativity parameter, but it's based on fundamentally different properties, the influence of size or polarizability. What this means is that the bigger nucleophiles are typically better. An example are iodine or selenium. And the reason for that is that a large nucleophile has a very diffuse electron cloud, and that electron cloud is easily deformable. So we can think of a nucleophile reacting with our substrate, and in the course of this reaction, this nucleophile can distort into something which matches the shape of the substrate quite well. And larger species are simply more prone to these distortions. The good analogy to think about is having small nucleophiles such as fluorine being hard tennis balls, while the large nucleophiles can be sort of big balls made of cotton, which are very easily deformed into whatever shape is required for the reaction to proceed. So in terms of size, the polarizability, again, the bigger the better. So iodine is better than bromine, which is better than chlorine, which is better than fluorine. And fluorine actually is not a very good nucleophile at all. And the same applies to neutral nucleophiles as well. Yeah? The next factor, which is sort of related to charge, but it's not quite the same thing, is factor number 4, and that will be the steric bulk. This is mostly related to organic-based nucleophiles, and it simply means that branched nucleophiles are worse. For example, if we have a methoxide anion, it will be a better nucleophile than the T-butoxide anion, because these three methyl groups will block the access of this nucleophile to the carbon center that is of interest. Now, an important point to realize this here is that both of them are good bases, right? Even though their nucleophilicity is very different, their basicity is almost identical. And the reason for that is that the proton itself is very small, right? And so proton can really squeeze in anywhere and attach to a carbon, almost no matter how sterically encumbered it is. Whereas with nucleophilicity, which deals with reaction of carbon systems, which are much larger, things are a little more subtle, and the nucleophilicity is strongly dependent on steric factors. And this is just one example where basicity and nucleophilicity are not identical. Okay? The final factor is that of solvation. And basically, solvation in nucleophilic reactions is bad because it blocks the nucleophile's charge. So if we have a fluoride ion and we put it into water, it will extensively hydrogen bind to water molecules, which will then shield some of its negative charge and prevent it from interacting. So solvation is bad. Okay? And so this is protic solvents are especially bad. And protic solvents are those which have hydrogens capable of hydrogen bonding, such as NH or OH bonds, are not good for SN2 reactions. However, this is a double-edged sword because most of the nucleophile, this fluoride minus, doesn't come alone. It comes with a counterion, it's typically sodium or potassium, something like that. And so most of the nucleophiles we're going to encounter are salts. And salts are really, as you remember probably from one of our first lectures, that salts are not soluble in hexane or non-polar salt. So you do need some sort of a polar solvent to dissolve the nucleophiles. But these polar solvents need to be aprotic, so that they will dissolve these highly polar nucleophilic compounds, but they will not hamper the nucleophilicity by extensive hydrogen. In examples of these polar solvents are things like acetonitrile, things that have a large dipole moment, but no hydrogens able to engage into hydrogen bond. So this will be one, acetonitrile. Acetone is another one. And two common solvents that are very common are this compound known as dimethyl sulfoxide, also known as abbreviation DMSO, and dimethyl formamide, and N-dimethyl formamide, also known by its abbreviation DMF. All these are examples of solvents which are polar, are highly polar, but have no protons capable of hydrogen bonding. All of their hydrogen atoms are attached to carbons. Okay? And just as an important point, which cannot be overly emphasized, is that H2O water is bad for SN2 reactions, because it will basically kill your nucleophile. In the next subtopic, we'll see how nucleophiles affect rates of SN2 reaction. Now we'll see how structure of substrate, especially the leaving groups, affect the rates of SN2 reaction.